Yes, so this is the overview talk of the First Stars program, and I will give you some science highlights after just repeating my own picture of the chemical evolution of the universe, which, as you all know, started with the Big Bang, where a few elements were created, hydrogen, helium, and lithium. A few 100 million years later, the first stars were formed, and the most massive of these exploded as supernovae and created the heavy elements that were incorporated into gas and led to the formation of a second generation stars. These second generation stars some of them were massive, exploded as supernovae. They led the rest of the chemical evolution of the universe, but some of them were low mass stars, and they are still alive today, and we found some of these. So this is the big picture of the First Stars project. I won't talk about the rest of the evolution of the universe with, galaxy formation and formation of Earth and ASTRO 3D and all this. But this is where I stop. So a different picture of the same thing is this. On the left are a few simulations of the formation of the first stars. And these are simulations of the initial mass function of the first stars. And I just want you to note how very different they are. That some of these predict that, oh yeah, all the first stars, they must have been tens of solar masses, even 1,000 solar mass. And others are more high-resolution simulations predict that, no, really, they could have been subsolar, and those stars should be alive still today. So the differences between simulations are enormous, but there are still some interesting things we can learn from this. So the simulations on the left by the two Japanese groups, those are zoom-in simulations on cosmological simulations, and they predict in which order the first stars should have formed. That they began already at redshifts of 30. And at redshifts between 20 and 30, you should have formed the most massive ones with maybe hundreds of solar masses. And only at later redshifts, down to, well, ending maybe at redshift of 10, you would have formed the less massive ones. So there's a hierarchy in when they formed, where they formed, and in the masses, but still all the numbers are uncertain. Depending on the mass of the first star, it should have ended in a different type of supernova. And depending on the supernova, you would expect different yields. So the chemical enrichment of the universe would look different. And that's what's shown on the right. And these predictions are there compared to individual extremely metal-poor stars back from the days of stamp collecting, when we found individual ones and we compared them to the abundances that were predicted from these supernovae. And then we were able to go back and say that the chemistry in this particular star came from this particular type of star, first star that had a mass of blah, blah, and that goes into forming an IMF. So this is pretty much what we want to do, except on larger scale. Within the center, we are simulating the first star's IMF. Indeed, one of these simulations by Pierre Sharda was created for ASTRO 3D, in ASTRO 3D. We also simulate the yields of the first stars, their supernovae and the AGB stars. And we're working on discovering the second generation stars and chemically characterizing them. And in order to do that, we have to also understand the physics of second generation stars. Things like stellar evolution, ready to transfer, how did their spectra form, how does that work, how do you actually measure the chemistry? And in the end, we want to connect the chemistry of the second generation stars back to the properties of the first stars. So I will show you a number of examples of this from the past year-ish, starting with Aldo's work on an extremely metal-poor star that has a very interesting chemistry. So it has a very low abundance of iron and other heavy elements, but the light elements are extremely abundant, overabundant. So the abundances of carbon, nitrogen, oxygen are very high. And this is exactly what you expect from population 3-star supernovae, the so-called Fink supernovae. The problem is that this particular star matches two entirely different models. One of them has no rotation, it's a classic model, and the other one is a rapidly rotating model. And the difference is in the abundance of fluorine, where the non-rotating model predicts basically no production of fluorine. The rotating model predicts so much fluorine that it actually falls outside the graph. And I had to add a little square just to show you how high it is. So if the rotating model would have been true, then you could have actually detected fluorine in the star. So Aldo took K-band spectra, and he's looking for a line that's actually weaker than the telluric lines. So you had to wait until like exactly September 22nd in order for the radial velocity to be just right, so it wouldn't be covered by tellurics. And he took a spectrum, and it shows the fluorine line, which doesn't agree with either of the models. It's somewhere in between, showing that the progenitor star, it's still a a fair match to the models, but it's neither not rotating, nor rotating. It's somewhere in between. So this is a way of pinning down the properties of the first stars in a particular rotation, which is very difficult. You just heard from Maddie. This is the other end of her work, which is that she's measured masses in globular clusters, not just once, but actually twice. So using astroseismology, she has measured masses in red giants and AGB stars, and also on the horizontal branch. And this allows her to measure the average mass loss in these stages. And she found that this actually evolves with metallicity. So that at lower metallicity, the mass loss is smaller. At higher metallicity, the mass loss is larger. And you can sort of feel that this should be happening because metals at opacity and radiative acceleration should shoot away more material when this happens. So it's a very nice empirical proof of how this works, as I understand, the first time ever. And yeah, just beautiful work. The other Maddie, who will speak next after me, has measured heavy isotopes of magnesium in old stars. And these are two completely different works here, and they're also different from the one she will be presenting. So I'll try my best, but in a nutshell, the one on the left is showing the chemistry of Milky Way halo stars and how these halo stars are either in situ, so born in the Milky Way halo, or they're accreted, so born in small galaxies that were accreted by the Milky Way. And depending on if they were born in the Milky Way or accreted, they have different chemistry. So the in situ stars are high in magnesium, high in alpha elements. And Maddie went out to measure magnesium isotopes and find that they're also rich in heavy isotopes. These are created in AGB stars, showing that the in situ stars are enriched by AGB stars, the accreted stars are not. And this tells you something about the timescale of chemical evolution in these systems. Her other work is on a globular cluster, which we just heard about the intricacies. This is a type 2 globular cluster, so it has something like 8 populations. So they differ in metallicity, they differ in sodium-oxygen abundances, they differ in S-process abundances, and it turns out they also differ in magnesium isotopes. So Maddie's work shows that the classical sodium-oxygen anticorrelation correlates with the magnesium isotopes, but the S-process production does not. And this is interesting because you expect having magnesium isotopes to be produced in AGB stars. AGB stars famously also produce the S process, run the S process and produce those elements. So for these two chemical signatures to not be connected, the S process enrichment must have happened in fairly low mass AGB stars, maybe just 2 solar masses. For more on Maddie's talk about the galactic chemical evolution, see her talk at the ASA in about a month's time. Leaving the Milky Way for a bit, my PhD student Wei Shen has discovered the 11 most ancient stars in the Large Magellanic Cloud. So not 11 of them, but the 11 top most metal poor stars ever found in the LMC. And he did this with the ANU 2.3-meter telescope. And his verification data shows that these extremely ancient stars actually rotate with the LMC disk. So they don't live in a halo, they actually rotate with the disk. So this is a bit unexpected, a little bit weird, but it proves that at least they are in the LMC. So Wei Shen requested UVS data. He was given a huge amount of observing time and took spectra of, this is 7 stars, I think. And these spectra show that the abundances on average look the same like in the Milky Way. But individual stars have very different abundances, showing that there's some kind of stochastic effect. Probably very few supernovae had gone off at this time. So there are large star-to-star variations. He also found this signature that the oldest stars, the most metal poor ones, have no europium at all. Europium is an R-process element, so it could have come from hypernovae, it could have come from neutron star mergers. So clearly no hypernovae in the early evolution of the LMC. But after a while, metallicities between -218 and -1.5, most of the stars are europium enhanced in the LMC, showing that something is producing a lot of R process with a delay, and that smells like neutron star mergers. So by comparing chemical evolution models to neutron star merger delay time distributions, we can pin down which one is the least inaccurate and how do neutron star mergers actually happen. Another one of my PhD students, Ben Lowe, is leading a survey of metal poor stars in our galaxy. So he's using the AAT with the 2DF instrument to survey metal poor stars that we selected from Gaia. And we are targeting the inner disk and the inner galaxy this time. So previously, we've used the 2.3-meter telescope over the past 6 years or so. We spent over 300 nights observing 5,000 stars one by one. And in the scope of about 8 nights, Ben's survey has blown this out of the water, of course, because the AAT has the 2DF instrument that can observe up to 400 stars at a time. And I'm showing on the right his first results from the first night, which was just 2 weeks ago. These are equivalent widths of H beta, which is roughly effective temperature, and the calcium doublet, which is roughly metallicity, showing that there are stars in there that are metal poor that we will want to follow up with a VLT to get chemistry from. And then finally, the thing that brings all this together, the glue of first stars, is StarFit, the code that is being developed by Alex Hager, which can take your measured abundances from whatever you want, a star, a quasar, anything, and it compares that to nucleosynthesis yield databases. So StarFit takes a lot of the thinking out of the equation. You don't have to understand.
2-minute warning.
Thank you. You don't have to understand how to treat your errors. You can put in your statistical errors like anyone would do, but also upper limits, correlated errors, and you can fit multiple databases at the same time. You can even combine databases. I'm showing an example in the left, which is comparing these databases to a quasar at redshift 3.4, which was the highest one with a lot of abundance measurements that I could find in the literature. XQR30, I'm looking at you, please give us more data, or we can help you use the code. So this is just the web tool produces this. I'm showing the website on the right. You can also download this or install it yourself. Pip install StarFit gives you the code, and you can just run this. So if you're interested in this tool, please contact myself or Alex, and we'll be happy to try to help you. And I'll just wrap up with my summary slide, which is just showing all these things that I've just talked about. And I'm happy to take questions. Thank you.